The finite element method's convergence issue on triangular and tetrahedral meshes violating the maximum angle condition is addressed. Standard conforming, nonconforming, and discontinuous Galerkin finite elements do not converge as the mesh size approaches zero, as shown by Babushka and Aziz. This issue is illustrated through two calculus examples, demonstrating that small triangles may not converge to the tangent planes of a surface. Nonconforming finite elements, with functions continuous up to the pk1 order, are introduced, but they also failed to converge on such meshes. A novel solution is proposed using the weak Galerkin finite element method, which converges on arbitrary meshes. This is achieved through a gradient-preserving Zhang transformation, a scalar version of the inverse Piola transformation. The WG finite element space is defined as VH equals V0, VB, V0 element of L2, TH, V0, T element of PK, T, VB element of L2, EH, VB, E element of PK plus 1, E, VB, partial differential omega equals 0. The weak gradient is defined as nabla WVH, Q, T equals V0, nabla dot operator Q, T plus n airy summation E element of partial differential TVB, Q dot operator NE, and by integration by parts, nabla WVH nabla V0, Q, T equals VB V0, Q dot operator NT. The finite element approximation problem is formulated as find a element of VH such that nabla WVH equals F VH for all VH element of VH. The key result is that parallel nabla V0 parallel 0 is less than or equal to C parallel nabla WVH parallel 0, where C greater than 0 is independent of the shape regularity and the size of TH. This result is proven by decomposing VH on the unit reference triangle or tetrahedron T into V1 plus V2 element of V1, T, plus V2, T. The analysis is distinct from typical error estimates, as the interelement error is converted to other errors inside elements. Local interpolation and projection are introduced directly to the error estimation of the H1 projection. The gradient-preserving Zhang transformation is crucial for the convergence of the WG finite element method on arbitrary meshes. Here is the combined summary of pages 58. The authors introduce a finite element method for solving the Poisson equation, employing the Zhang transformation to construct a gradient-preserving mapping from a general triangle or tetrahedron to a reference element. This transformation, denoted by equation 2.8, preserves the gradient, and the authors prove lemmas 2.1 and 2.2 to establish a lower bound for the norm of the gradient and the uniqueness of the solution to the linear system of finite element equations. The convergence analysis is presented in Theorem 3.1, which provides an error estimate for the finite element solution in terms of the L2 norm and the H1 seminorm, bounded by Ch(k) plus 3. The proof involves testing the Poisson equation with a function from the finite element space, applying integration by parts, and using the definition of the weak gradient, along with the local L2 projection operator QH and the L2 projection operator πk plus 1. Moving on to the analysis of the interpolation error estimates, the authors develop a novel finite element method based on the BDM interpolation operator IBDM. The operator is defined by three conditions, and the authors show that the difference between the interpolated gradient and the true gradient can be bounded by the size of the element and the Sobolev norm of the function. The numerical test results for the 2D and 3D Poisson's equation on quasi-uniform and degenerate meshes demonstrate that the P1 conforming finite element method converges at the optimal order in L2 norm and is superconvergent in SEMA1 norm on quasi-uniform meshes. However, under non-uniform refinement, the solutions do not converge at all, indicating poor performance of the P1 conforming finite element solutions. The finite element method's performance in solving Poisson's equation on 2D and 3D domains is examined, focusing on P1 conforming and P1 weak Galerkin methods. Error profiles and convergence rates are presented for quasi-uniform and degenerate meshes. The P1 conforming method exhibits optimal L2 convergence and superconvergence in SEMA1 norm on quasi-uniform 2D meshes, but lacks robustness when refining meshes in one direction. In contrast, the P1 weak Galerkin method demonstrates superior performance, achieving 2 orders above optimal convergence rates in L2 and Semma 1 norms on both quasi-uniform and degenerate meshes. In the 3D case, the P1 conforming method shows suboptimal convergence rates, while the P1 weak Galerkin method maintains its superior performance, achieving 2 orders above optimal convergence rates in L2 and Semma 1 norms on both quasi-uniform and degenerate meshes. Visual representations of the meshes are provided in figures 2 and 3, illustrating the differences between quasi-uniform and degenerate mesh configurations. The P1 weak Galerkin method's performance is attributed to its formulation, which allows for the use of discontinuous elements and a stabilizer-free approach, enabling superconvergence. The error profile for the 3D P1 weak Galerkin method is presented in Table 4, showcasing its accuracy in computing the solution. The method's robustness and efficiency make it a suitable choice for solving elliptic problems on various mesh configurations. The authors provide a comprehensive list of references, citing relevant works on discontinuous Galerkin methods, nonconforming elements, and weak Galerkin methods. The paper's technical content is supported by a rigorous mathematical framework, ensuring the accuracy and reliability of the results.